Good morning, everyone. My name is Ibrahim Aman Sayed. Today, I'll be presenting a crucial topic at the intersection of cybersecurity and machine learning, specifically how we can defend graphical neural networks or GNNs against one of the most dangerous types of attacks called backdoor attacks. So my topic, which I borrowed from an esteemed professor from Beijing Institute of Technology, is Dr. Xinguang Liu and many others accredited. The topic is D-Shield, defending against backdoor attacks on graph neural networks via discrepancy learning. As machine learning models are becoming increasingly used across sensitive domains like social networks, finance, and healthcare, protecting against them, protecting them against manipulations becomes essential, basically. So let's start with the table of contents. First, we're going to follow a flow that starts from introduction, and we're going to jump into background and related work, then thread model and design goals. Then I'll guide you to the motivations of it and the capabilities of how both attacker and the defender uh, happens. And then I'll guide you to D-Shield itself, how it's designed, how it detects poisonous nodes, and how it reconstructs a clean, secure model. Then we're going to look at experimental results, and we're going to validate its effectiveness. Then we're going to discuss its drawbacks and future improvements. Then the rest of it is insights and conclusions and everything. Okay, let's get into the introduction, basically. Think about how your social media accounts link you to your friends, or how banks show you connections between accounts. These networks basically are graphs. The graphs are everywhere. Even when we do simple tasks online, these GNNs they help us learn from these connections by looking at each item's features and how they connect with each other. But here's the problem. Sometimes some people, hackers or bad actors, they try to sneak in small hidden change in data during training, and this is called a backdoor attack. Normally, the network works well, but if the secret trigger appears later, the network can give wrong answers on purpose. There are two types of attacks basically. One of it's called dirty label attacks. The other one is called clean label attacks. Dirty label attacks changes both the data, features, and the labels during training. The second one, they only change the features while leaving the same, what do you call, while leaving the same, how do I call, while leaving the same label, um, but it changes the features. Okay, let's begin by understanding how a backdoor attack works. Um, there are two types of backdoor attacks, like I said before. Um, Dirty label and clean label. Backdoor attacks are basically the attacker basically they have a graph construction. The attacker carries it out. The attacker carries a normal looking graph and they check how many users are using it. They select a small subset of nodes to target. These nodes are modifications and they act as hidden triggers. They're unlikely to be noticed during causal inspection, but later it's going to be known that it's a poison graph because changes are in slight number and the number of poison nodes is small compared to the overall graph. The model basically learns normally, by achieving good performance on validation. However, the trap is set, but when a similar trigger pattern appears during testing or deployment, the model's behavior shifts dramatically, often classifying malicious attacks as trustworthy or normal as malicious. Okay, let's look into the background and related work. A backdoor attack on a graph GNN is a hidden type of attack. It's a hidden attack where someone secretly changes the training data so that the model learns um, a hidden weakness. Later, when a small specific change is added during testing, the model behaves incorrectly, such as making wrong predictions. Even though it looks normal, it's not. The goal of the attacker is basically plant weaknesses without making it obvious during training. Okay, in a typical backdoor attack, the GNN, the attacker first builds the graph, then picks certain nodes to poison. Poisoning means they either change the features or modify the nodes or graph structure or something. Then they train the GNN on this poisoned graph. Once the model has learned from this poison graph, it basically works normal for most of the time. But when an attacker later applies the same trigger during testing, the model um, it gets fooled and gives the wrong output. As we spoke about, we have two types of attacks, DLBA and CLBA. And okay, the currently existing defenses are three types: pre-process defenses, detection defenses, and poison suppression defenses. Okay, before there were a lot of like strategies. Before DShield, there were several strategies. Let's talk about the first one, pre-process defenses. Here, defenders they attempt to clean the graph before training by removing like suspicious edges or nodes. While this can work against some obvious attacks, um, sophisticated attacks can basically craft the changes to appear like normal, and they can bypass these defenses. The second line of defense is called detection-based attacks or detection-based defenses. After training the model, the defenders analyze the node behaviors to find anomalies that might suggest a backdoor, basically. The third strategy is to poison suppression during training. Like the labels smooth or like, but they smoothen the labels or lessen the influence of the poison nodes by assuming that it's just noise or just something else. And it often leads to a little bit drop of performance, but they're basically too cautious. Okay, let's dive into threat model and design goals. To properly defend against backdoor attacks, we must basically clarify and understand how the threat model works. In other words, we have to know what like the attacker's powers are and the defendant's powers are, like what each of them can do. The attacker has more power usually because they have full access to the original graph and are able to insert like polished nodes or edges by embedding hidden triggers. However, there are important limitations on the knowledge, and they do not know what specific model the defender will train, nor do they know like what defensive measures might be applied. This like uncertainty limits the attacker's ability to like adapt the strategy. On defender's side, it's much more challenging. Defenders only receive the graph, which may already be poisoned. They don't even have the knowledge of it, and they can basically like they can find a way to like defend against direct clues. Basically, the defender is much of less power over here than the attacker. There's a very big asymmetry over here, being the attackers know everything and defenders being in the dark. This defines like a real world problem. Given these conditions, DShield has a clear goal. Um, it must work without like assumptions about the attacker's method, the nature of the trigger, or even the extent of poisoning. DShield needs to be general, it needs to be robust, and it needs to be capable of adapting to different types of attacks. The main ideas that were kept in mind while developing DShield were um, when DShield was built, um, it focused on defense basically. DShield was different from other approaches. Um, what it did was the first model, it had two models, right? The first model it trained in supervised way, the other one it trained in semi-supervised way. The difference between these two is called semantic drift, and similarly, the poison nodes may show like abnormal emphasis on certain features. It shows that something is wrong when comparing these two. After like measuring these discrepancies, DShield like basically applies clustering techniques to group together suspicious nodes, and then we can know like only truly the poison nodes are removed, leaving the clean ones untouched as much as possible. So basically, DShield works without knowing what the attacker's trigger was and what happened behind the scenes. Next is the proposed method, DShield. Okay, so let's dive deep into DShield. It basically has three main parts. Let's go into the first part, which is called auxiliary model training. The first part is our approach to train two different models using the same graph. The reason for doing it is to get two separate views of the data. One model, which we call the backdoor model, is trained in a way that mixes labeled and unlabeled data. The other one This is called the semi-supervised learning approach because this model is trained on all available data, including the data which might be poisoned. It learns in a way similar to how like a typical graph GNN would learn. Yeah. The second one is a self-supervised model. This model is trained differently because it does not rely on human labeled data at all. Instead, it uses the concept of contrastive learning and reconstruction laws. So, contrastive learning, we give the model different views or slight variations of the same graph. The goal is that even these small changes, the model should create similar internal representations. This forces the self-supervised model to focus on like underlying patterns in the data. We also use reconstruction laws. It basically means that the loss function makes sure that the model can recreate or rebuild the original features of the graph from its original representation, from its internal representation. By doing like that, the model reinforces its understanding of the of the graph's inherent like structure. So combining these two, they provide a beautiful comparison of the model. The discrepancy matrix. Okay. So let's get into the second part, which is the discrepancy matrix. In this step, we compare basically the behavior of two models that we trained earlier. One is backdoor and the other one is self-supervised. Um, the goal here is to spot the difference between them. First, we look at what is called semantic discrepancy. Think of like every node in a graph having internal fingerprint made up of like features, different features. And it tells us when a shift happens between the two models. The next one is attribute importance discrepancy. This simply means that we're checking features or attributes of a node which are too much, which has too much weight in the backend, and we compare it to the self-supervised one. The data of this one is stored in the featured emphasis shift matrix, and the data of the semantic discrepancy is stored in the semantic shift matrix. Okay, let's get into backdoor free model training. Once we have detected possible poison nodes using our discrepancy matrices and everything, we move on to the next major step. Here we identify the target label. The attacker like tries to push certain poison nodes toward a specific label. For example, attacker might uh, want the model to incorrectly classify some nodes as trusted. And yeah, here we identify them. The second one is we filter the nodes, like we suspect them of being poisonous. Then we retrain the model. With the poison parts removed, we train a new model using only the remaining parts. Then we process the final result after that, which is a secure, reliable, and accurate model. Okay, let's go through briefly over the timeline of B-Shield. Firstly, we start with the input. Okay, the possibly poisoned graph. At this point, like no assumptions are made about the nodes or cleaned or poisoned. Both supervised and self-supervised models are trained in parallel. This ensures that learning differences between models are available for comparison. And once the discrepancies are computed, clustering algorithms are applied to them to identify groups of nodes that behave like similarly. And we also like make a list of those which deviate from the normal patterns. Then next step is to remove these poisonous nodes selectively and finally do a clean model training, which is done only using the remaining trusted nodes. And next step. Okay, let's dive deep into auxiliary model training. To fully understand like what a D-Shield does, we need to look at how auxiliary model training is done. Okay, so basically, the two key models, supervised and semi-supervised models, are trained. Supervised models is taught in a way that's usually like machine learning models are trained. And the other one, what we do is we tamper with the labels. So the model might end up learning some misleading behaviors, especially when it comes to like intentionally poisoned ones. The self-supervised model does not use any of these labels at all. Instead, it just depends on two important techniques. One technique is called contrastive learning. And yeah, by using these techniques, it simply means that the model is shown very two similar things of the same thing, basically from different angles, like same picture from different angles. And it basically notices the underlying patterns behind it. By this way, we can like find the actual thing to focus on rather than just memorizing the surface details. Okay, the next step is experimental evaluation. After creating D-Shield, the research team, they know that it was important to like check if it really worked in real life situations or not. So they designed a large set of experiments that focused on like five major questions. R1, R2, R3, R4, R5, effectiveness, robustness, sensitivity, ablation studies, and graph classification attacks. So first, effectiveness, they wanted to know if D-Shield can greatly reduce the success rate of backdoor attacks while keeping the accuracy. And the second one was robustness. They tested whether it worked under tougher conditions, like if they had higher number of poison nodes or not, when they had higher number of poison nodes. And third one was they looked at the sensitivity. This means they wanted to understand how much its performance depended on different settings. Um, and the next important thing was ablation studies. In these experiments, the researchers they removed or changed different parts of the shield and wanted to check if find out if which parts are necessary for the shield to work. Yeah, basically that's what happened. And generalization, the last part, graph classification attacks. It tested whether T-shield can be helpful only for tasks which the model needs to classify individual, how do I say, like individual nodes, but also for tasks where whole graphs are classified. Generalization was very important considering like practical applications in other fields like biology and chemistry and these fields. Okay, we basically used five data sets, out of which three are very important: Quora, PubMed, and Flickr. Let's go to these three. Go through these three. Quora is like a classical citation network where each academic paper is a node and it links between them and indicate whether the paper cites another or not. So Quora is relatively small and easy to manage. That's why they use the Quora in that. Next one is PubMed. PubMed is a citation network, but it's large and more complex. It's almost like the same thing as Quora, but it's more larger. And it has a richer like citation network. The third one is Flickr. Flickr has images. It's basically made image sharing website, and it's quite different from citation networks. The nodes might represent users or images, and these links could show friendship between the shared interests. Okay, let's go into how they measured the success. They basically used two main metrics. The first one was attack success rate. The second one was accuracy. Okay, so the attack success rate was basically to see how often an attacker can trick the model after like a backdoor is attempted. Imagine that an attacker has tried to sneak in a secret trigger into the data. It sees whether the model can be fooled by that or not. And attack success rate should ideally be zero, which means that um, the success rate is almost nothing. And D-Shield basically succeeded in avoiding all the attacks. The second metric we use is accuracy, or ACC. This measures basically how the model performs when there's no attack happening, and it's supposed to be almost the same as the usual data. It's supposed to be like, and this one we found like it was different by 1% or 2%. That's it. And this balance is very important because um, some defenses might stop many attacks, but in a way to do so, we need to make sure that the overall system is reliable or not. Okay. Okay. These are two pictures from the paper that I took. It basically compares different types of attacks: SBA, GTA, and EBA, GBF, GSM, and all of these. SBA basically stands for simple backdoor attack. GTA stands for graph Trojan attack. EBA stands for edge-based backdoor attack. GBF, GSM stands for graph-based fast gradient sign method. And these methods basically it showed ASR and ACC for both of those, and it compared with everything. Okay, this is basically the simplified version. The success rate, like before defense, was very high. It was very high, and the attacks were happening very frequently. After D shield was applied, it dropped down to like it dropped down like 80% basically. So it wasn't successful at all. Like it drastically changed the overall thing. And yeah, here we can see basically this graph in a simplified way, like the three um, main, what do you call, the data sets, and the accuracy was almost the same before and after. Okay. The drawbacks, like every model, this model also has drawbacks. It needed extra time in computation because it had two training models at the same time, and it was heavier and way slower than that. And second one was it had difficulty with clever attacks, basically like small attacks which might not be even noticeable. It had problems with that. Um, it also had problems with rare labels. Rare labels are where data sets have very less labels, and it couldn't classify if they had no labels. So these are the main three drawbacks which it had. And looking into future research, we can see that D-Shield model trains like full self-supervised model, like contrastive learning and reconstruction loss. This means that every node in the graph system works very hard comparing different views by trying to rebuild the original features and everything. One possible improvement can be that it would be to run the self-supervised training only on the parts of the graph that look suspicious instead of the whole entire graph. Okay, the second one is handling very stealthy attacks. Some attacks are extremely stealthy, like causing only very few changes in the model's internal signals. If the difference between a poisoned attack behaves like how clean node behaves, it's very tiny. It cannot differentiate. Um, by this, we can say that we need a hard triggeredness, which alerts basically when you can hear a volume turning up, and instead of a quiet sound, we can hear a volume turning up. This way, like we can see slight changes from like super stealthy attacks might be picked up more easily. And improving clustering. This algorithm basically has an unsupervised clustering algorithm. We can move it to a supervised one. That's the easiest way the model can be improved. And yeah, basically, these are the things. And let's talk about discussions. It showed impressive results with the main three data sets we discussed about. And yeah, it dropped down the percentage like 80%, like we spoke about the attack success rate. And the accuracy it only changed by like 1%. And it's good on like handling adaptive attacks. That's the second point. Attackers are always trying like new tricks. Um, it's very adaptive to the new tricks as well. Its sensitivity and ease of use. Um, it's not too much precisely tuned, such as like a beta and gamma things are not precisely tuned. That makes it like easier to use. Okay, let's get into the insights. What I learned from this was like trust issues in training data. One of the biggest lessons is that machine learning models cannot be trusted, and it can be attacked while the training process, not just that they're put into work. Attackers can like secretly poison the training data by adding small hidden patterns across the graph. The model learns from this training data without even realizing it, which makes the problem even more dangerous. Okay, the other thing I learned was how poison nodes behave differently. When nodes in a graph are poisoned, they behave oddly inside the model. Yeah, that's how like it's easier to spot the differences. Okay, let's talk about the role of self-supervised learning. Self-supervised learning is a powerful ally to find these hidden attacks, but this approach allows the model to see the real relationship between the nodes without being like misled by tampered data, which makes it easier to spot, if anything. And the next thing is it balances security and performance very well. It doesn't affect the performance very well by reducing the security by improving the security by a lot, basically. Okay, let's get into the conclusion. In conclusion, I would like to say that the world is basically it depends more on digital systems nowadays. The digital systems are deeply interconnected. Maintaining their safety is more critical now than ever, and D-Shield is a promising step in that direction. It shows us that with careful design and smart methods, we can build defenses that can protect the networks even from the most subtle and adversarial attacks. And by this way, we can ensure that models remain secure and reliable in today's digital environment. So yeah, that's pretty much it. These are the references which I took. And yeah, this is my presentation. Thank you very much for listening. My name is Ibrahim, and this will be signing off. Thank you so much.